Hello everyone, this is Aminur Rahman and welcome to the PhysX project. We talked about the basics of projectile motion in the previous video. If you haven't watched it yet, do check out the AS playlist on our channel. You will find it as the first video in this series. Today we are going to derive the equations of projectile motion. Let's dive in. Before we start deriving, let's quickly refresh our memory on finding perpendicular components of a vector and also finding the resultant vector from perpendicular components. This video is not to discuss those concepts in details, rather just a quick recap of our knowledge regarding components. Let's say v is a velocity vector, vx is its horizontal component, and vy is its vertical component. If this side of the rectangle is vy, this side is also vy. Similarly, this side is vx. Now, if v makes an angle of theta with vx, then cos theta equals adjacent over hypo or vx over v. Therefore, vx equals v cos theta. From the same triangle, sin theta equals opposite over hypo or vy over v. Therefore, vy equals v sin theta. But if theta is given with vy, sin theta equals opposite over hypo or vx over v. Therefore, vx equals v sin theta and cos theta equals adjacent over hypo or vy over v. Therefore, vy equals v cos theta. The important thing to remember, the component that makes the angle with the vector is the cosine component, and the other perpendicular one is the sine component. Many students mix this up by memorizing horizontal equal cos, vertical equals sine, which isn't always true. Just check the diagrams and let trigonometry guide you. Now let's quickly recap how to find resultant from perpendicular components. Let's say one component is Vx and the perpendicular one is Vy. The resultant would be the diagonal V of the rectangle formed by those sides. If V makes an angle of theta with Vx, we can use Pythagoras to find the magnitude of the resultant V and trigonometry to find the angle or the direction. Now let's move on to deriving the equations for a projectile motion. Let's take a point A on the ground. A projectile is launched from A with an initial velocity of u and with an angle of alpha with the ground. The projectile follows a parabolic path and lands back on the ground at point D. The horizontal component of u is ux and ux is u cos alpha. The vertical component of u is uy and uy is u sin alpha. From the previous video, we know there is no horizontal force on the projectile if air resistance is ignored, so horizontal acceleration ax is 0. The initial vertical velocity component is upward and so are the vertical displacements at every point on the pathway. So we will consider upward direction to be positive. Therefore, vertical acceleration ay is negative g as it acts downward. We will keep this table handy. It's our reference for the rest of the derivations. Let's consider a point P with coordinates xy on the path of the projectile. It means that the horizontal displacement for the point is x and the vertical displacement is y. To derive the equations for these displacements, we are going to use the basic Schubert formula S equal ut plus half at squared. As the projectile motion is a two-dimensional motion, we are going to use two different versions of this Schubert formula to find the horizontal displacement and the vertical displacement. For the horizontal displacement, we are going to use x for s, ux for u, and ax for a. Time t is not affected by horizontal or vertical version as time is a scalar quantity, and so there is no issue of components associated with that. For the next line, we are going to replace ux with u cos alpha and ax with 0 from our table. Therefore, horizontal displacement x equals u cos alpha into t. For vertical displacement, we are going to use y for s, uy for u, and ay for a. For the next line, we are going to replace uy with u sin alpha and ay with negative g from our table. Therefore, vertical displacement y equals u sin alpha into t minus half gt squared. There's something very important to notice here. The equation for horizontal displacement is basically S equals Vt. We use this equation to find the displacement of an object that is moving with uniform or constant velocity. For a projectile motion, the horizontal motion is actually a motion with constant velocity, as there is no acceleration or deceleration if we consider the air resistance to be 0. Now let's take the final velocity at P after t seconds from the launch to be v. Its horizontal component is Vx and the vertical component is Vy. To find the equations for these velocity components, we will use the Course-Suvart formula v equals u plus at. We will use the horizontal version of this formula to find the horizontal velocity component and the vertical version to find the vertical velocity component. For horizontal version, we will use Vx for v, ux for u, ax for a. From the table, we know that ux equals u cos alpha and ax equals 0. So we get Vx equals u cos alpha. Notice again that the horizontal velocity component is independent of time, meaning it remains the same no matter which point of time you are talking about during the whole journey. Horizontal motion is like that one student who never changes. Same speed, same attitude, no matter what's happening around. Now for vertical version, we will use Vy for v, uy for u, and ay for a. From the table, we know that uy equals u sine alpha and ay equals negative g. Therefore, Vy equals u sine alpha minus gt. So we have got our perpendicular components of v. To find the magnitude of v, we will use Pythagoras. Now if v makes an angle of theta with Vx, then we can use trigonometry to find the direction. Now we will derive the equations to find the time it takes to reach the maximum height and the maximum height itself. If you observe the pathway, you can easily understand that the maximum height is right in the middle of the pathway, and the pathway is symmetric about that maximum height. If you watched the video closely so far, it should be already permanent in your head that the horizontal velocity component remains the same throughout the journey. But the vertical velocity component decreases for the first half of the journey and increases downward for the second half because of acceleration due to gravity. Its maximum height is when the vertical velocity component becomes 0, so it cannot ascend any further and starts descending. We will use this knowledge to find the equations. To find the time it takes to reach the maximum height, we will use the Course-Suvart formula v equals u plus at. We will use its vertical version. As we discussed already that the final vertical velocity component at max height is 0. We will use 0 for Vy, and from the table, uy is u sine alpha and ay is negative g. If we make time to be the subject, t equals u sine alpha over g. To find the maximum height it reaches, we will use the Course-Suvart formula v squared equals u squared plus 2as. We will use its vertical version. We will use 0 for Vy, u sine alpha for uy, and negative g for ay, and replace y with h max. If we make h max to be the subject, h max equals u squared sine squared alpha over 2g. Now let's derive the equation for total flight time. Total flight time is the time from launch to landing, the time it takes for the whole journey through the air. We will approach it from two different perspectives. Let's start with approach 1. Projectile motion is like a perfectly choreographed dance. Horizontal and vertical motions are independent, yet in a perfect sync, creating that elegant parabola. If you observe that elegant parabola, you will notice that the max height position is right in the middle. So total flight time is exactly twice the time taken to reach the maximum height. We already derived that time to reach max height is u sine alpha over g. Therefore, total flight time equals 2u sine alpha over g. Now approach 2. For this one, we will use the vertical version of displacement equation. Look at the diagram again. The projectile starts from A, lands at G. So its vertical displacement is 0 after the whole flight as it returns to the same height level. So we will use 0 for vertical displacement y, and you should already be quite familiar with rest of the substitutions. Therefore, total flight time T total equals 2u sine alpha over g. It is very important to remember that this equation is not applicable if the landing height is different from launch height. In those cases, you can use the second approach and use the vertical displacement of the landing point instead of 0. It will work just fine. Now we are going to derive the equation for range. Range is the horizontal distance an object travels before hitting the ground. So that's the distance AG in the diagram. Range is the product of horizontal velocity component and total flight time, as there is no acceleration or deceleration involved for horizontal motion. We know from the table that Ux equal U cos alpha, and we just derived that T total equals to U sin alpha over G. So range equals U squared sin 2 alpha over G, as 2 sin alpha cos alpha equals sin 2 alpha according to trigonometry. We also know from trigonometry that the value of sine of any angle is in the range of -1 and +1, where +1 is the maximum possible value. So for maximum range, sine 2 alpha should be equal to 1. If we consider U to be constant for every launch from the same location, we can replace 1 with sine 90 degrees. So 2 alpha equals 90 degrees. Therefore, alpha equals 45 degrees. So if we keep the initial velocity constant and vary the angle with the horizontal, the projectile will travel the maximum range when it is thrown at an angle of 45 degrees with the horizontal. Therefore, maximum range equals U squared over G. Now that's my time for today. In the next video, we are going to solve some exam-style projectile motion problems. Thank you for sticking around. See you in the next video.